Okay, let's start. So this is the first course where we are going to introduce radar systems. You can see the outline of the lesson. We'll be talking about radar principle and range measurement firstly, and then we'll look at radar waveforms in time and frequency domain. Then we'll introduce some basic radar parameters, and there is going to be a short derivation of radar range equation, and then we'll conclude with some radar applications and examples. This material is compiled from Skolnick's book, third edition, so it is basically most of the material in chapter 1. Okay, here we see an illustration showing how a radar system works. This is a very high-level illustration. As you might know, radar stands for radio detection and ranging, radar. And the idea is quite simple. We transmit a signal, a waveform. It travels in space and hits on a subject or a target that we want to see, and then return to the transmitter, so the location where we transmit that. And we simply count the time elapsed to determine the range to the target. Okay? As you see, the idea is very simple, but when you want to detect the target and try to measure its speed or other properties, then that's not that easy. You have to please turn off your microphone and speakers. It's not that easy when you want to see more details about the target. And that's why radar systems are simply known to be very complex. Okay, so how to determine range? Here we see simple geometry where we got a radar here and we have a target. An electromagnetic wave is transmitted from the radar. It travels in space with the speed of light, because electromagnetic waves travel at the speed of light, and it hits on the surface of the target and then return to the radar. Usually, transmitter and receiver are co-located. So in a typical radar system, we got transmitter and receiver. They are co-located. And then this echo signal is picked up by this receiver. Since we know the speed of the electromagnetic waves, we can determine range if we know the time elapsed. Okay? And usually we got a counter here. So simply a clock. It simply counts the time in nanosecond or microsecond or millisecond, depending on the system. And then we measure this TR by this counter, okay? Once we measure this TR, it's quite easy to determine R, the range to the target, okay? Simply speed of light times the time elapsed divide by 2, because why we use 2 here? Because we got two-way, you see, traveling. 1 hour to the target, and then 1 hour to the radar again. So 2 hours, simply 2 hours equals speed of light times the time elapsed. Okay, from here we can determine range. Okay, any question? Okay, let's see radar signal, radar waveform. What kind of waveform we are supposed to transmit so that we can measure that distance. Typically, a radar uses a pulse train, okay, pulse train, so sequence of pulses. As you can see on the slide, we got a pulse with duration tau, okay, and the distance over time between the pulses is called pulse repetition interval, or PRI, which is very critical parameter of a radar system. Okay, so if we remember the previous slide, if there is a target, when I send this pulse, this is transmitted pulse, let's say, then we expect an echo signal, right, from the target, which is located at a distance of r, and this distance is simply CTR over 2. So over the time, the echo signal from this pulse will be at a distance of TR, let's say. Okay? So, since we know this TR, we can determine R. So, we measure TR and then estimate R. Okay? So, if we continue transmitting pulses, then it's expected that we see the target almost the same distance, right? If it is not moving, if it is stationary. If it is not stationary, then we expect that this echo signal will be moving to the right or left. Okay? So what other parameters can we use here? First, we define pulse repetition interval, TP, okay? And since this is a period, we can define frequency as inverse of this. So 1 over FP, which is called pulse repetition frequency, okay? So then that's quite easy. If I know pulse repetition frequency, I know PRI, pulse repetition interval. They are inversely proportional. So then whenever we talk about the radar system, we might use either PRF or PRI. And we know that one can be obtained from the other easily. So it's better to use just one, PRF or PRI. Sometimes PRI, sometimes PRF. Okay? So how about the power? Typically, there are two power definitions are used in radar systems. One is average power, P average, which is the peak power given as peak power. Peak power simply the peak power of this pulse. So the maximum power of the pulse. So peak power and average power. These are the power definitions that we use in radar systems. Then the average power can be written as peak power times the pulse duration divided by pulse repetition interval. Okay? That's the ratio of the pulse width divided by PRI. Okay? So then smaller the pulse duration, right, for any TP, smaller the pulse duration, lower the average power. And here, this ratio, tau over TP, so the pulse duration divided by pulse repetition interval, is called duty cycle. Okay? Duty cycle. We can also write pulse energy from the energy formula, the pulse power times pulse duration. Okay? So in this case, for example, since this is rectangular shaped, right? The energy of this pulse will be the area. Okay? If it is given in power, so if this is the PT, the peak power, so just take a rectangle like this. This is PT, okay, peak power. And this is not correct. I'm sorry. Better to use this one. Here is the peak power, PT. So this is PT, while this is tau. So PT times tau gives you area of this rectangle, which is energy. But in practice, they may not be just a rectangle. This is quite an ideal waveform. In practice, it is quite distorted. But mostly, we can take the peak power times pulse duration. This is from the definition of energy. Energy is equal to power times time, right? Okay, we got a problem here. That's quite easy. We got an airborne pulse radar. Airborne, do you know the meaning of airborne? So it's about air. So flying platforms, right? Airplane, helicopter, unmanned vehicles, air vehicles, such platforms moving in space, and we want to detect them, for example. Then that type of radar is called airborne radar, or a radar installed on a platform which detects the objects over the ground or in space. That's airborne radar. It's pulsed radar, which means that it transmits pulses, okay? So it is just like in previous, the case in previous slide. It has a peak power of PT, 10 kilowatt, and uses 2 PRFs. So it seems that this radar switch between 2 PRF, not constant PRF. One is PRF P1 and P2, which is 10 kilohertz and 30 kilohertz. And what are the required pulse widths for each PRF so that the average transmit power is constant and is equal to 1.5 kilowatt. Okay, this is equivalent to 1.5 kilowatt. So we simply use this formula. I'm not going to solve this. That's a problem. You have to try this later. But you see the formula here. You know the definition of each symbol. Once you know them, then you can easily calculate this. Okay, that was the simplified radar waveform that we have shown previously. Now we are going into the details of that simplified radar waveform. So what do we have? Can be seen on this slide. Remember that we illustrated radar waveform as pulses like this, right? Now, we have actually a cosinusoid inside these pulses, okay? We actually transmit a cosinusoid with a limited duration, okay? Which looks like a pulse inside the cosinusoid, or pulsed cosinusoid, okay? Pulsed cosine. This is real radar waveform that you can measure in space, okay? So then we can draw, we can illustrate again more realistic radar waveform. Then we have one more parameter here, which is the frequency of the cosinusoid. Okay, we know the amplitude of this cosinusoid, which is PT, if this is power. If this axis represents power, then that's going to be PT, peak power. Now we have to define frequency and then period of this carrier. Okay, and typically the frequency of this cosinusoid is quite high. Okay, mostly on the order of gigahertz. Okay, gigahertz. So 1 gigahertz, for example, 1 gigahertz means it's equivalent to 10 to the power 9 hertz. Okay, so if we take a sinusoid, okay, here, if its frequency is 1 gigahertz, so 10 to the power 9 hertz, then this is going to be minus 9. Let's define both. Now we simply switch to time domain, which is 10 to the minus 9 second, which is 1 over 10 to the power 9 hertz. So we define then period, okay, which is 1 over frequency of this carrier or cosinusoid, okay? This is from basic signals, as you know. Then, if we try to summarize what parameters we have here, for a pulse train, we got peak power, right? Average power, right? Pulse width, and what else? Pulse repetition interval, which is inversely proportional to pulse repetition frequency, and duty cycle, which is tau over Tp, energy of the pulse, and carrier frequency, which is proportional to the period, inversely proportional to the period. So these are the basic parameters of a radar waveform. Actually, most of the significant parameters are listed in here. But when we consider more complicated waveforms, then we introduce some new parameters. Is there any question? Okay, good. So it was the time domain that we have been talking about radar waveforms. In this slide, we have time domain radar waveform and its spectral equivalent. So it's equivalent in frequency domain. Okay. Here we see a radar waveform whose, for example, peak power is Pt, the duration of the pulse is tau, and pulse repetition interval is Pr, which is 1 over pulse repetition frequency. Okay, it has an energy of EP, for example. It has a carrier frequency of Fc. These are the parameters that we have learned so far. Now, what is its frequency domain equivalent? This is a pulse train modulated by a cosine, or cosine modulated by pulse train. And to find its spectrum, we have to use a transformation. Okay, please go back to the communication systems course. How do we find frequency domain equivalent of a time domain signal? We use Fourier transformation. Fourier transformation. Okay? So as long as we write this waveform, then we can take its Fourier transformation to get its frequency domain equivalent. When we do this, we got a waveform shown on the right-hand side. Okay? So simply this is a waveform that's quite common. You have seen this in communication systems course. What was the name of this waveform? Sinc function. Good. All of you remember this function. That's why we studied that much in communication systems course. This appears everywhere. Okay? Not only radar, communication signal, digital signal processing, biomedical, everywhere. So it has simply a sinc type waveform that we are talking about. How about if we consider a cosinusoid only? Okay, from minus infinity to plus infinity. What is its Fourier transformation? Simply, what is the Fourier transformation of this function? Do we remember this? Again, Fourier transform, direct delta. If you write into sided, then it's going to be 1 over 2 direct delta f minus fc plus direct delta f plus fc. One-sided version is going to be direct delta f minus fc. Right? So if we show it, if we draw it, then it's going to be simply, if this is the frequency domain, then there's going to be a direct delta here at fc. Okay? Whose amplitude is 1. However, when we want to take Fourier transformation of a cosine, if you want to take this, you have to limit your cosine, right? It cannot be infinite to the left and right. You have to stop somewhere because you have a limited capacity of calculator, right? You have a memory. You have to put the data there, but you have limited size. Then you have to use limited number of samples over your cosine. And then you take its Fourier transformation. So what will happen if you limit this cosine? If you limit this cosine with a t, let's say, then this direct delta will be spreading, will be distorted into some kind of sinc function. Okay, sinc function. Then the spectrum will look like this. Okay. Very narrow sinc. Why? Because we take a long t. Okay? And long t means, you see, this first zero of sinc function is proportional to pulse width. Okay? If I choose a very big tau, then this sinc will be simply what? Smaller. When it is infinite, it's going to be single direct delta. So when you try to measure spectrum of a cosine in the laboratory, then you expect a direct delta theoretically, but it cannot be a direct delta. So typically it looks like a sinc function. Okay? But very narrow sinc function. Okay? And tomorrow, or the day after tomorrow, I'm sorry, and next week, you will be experimenting some radar waveforms in the laboratory where you will see how a radar waveform is transformed into frequency domain or measured in frequency domain and how it looks like when you change its parameters. Okay, so from here then, if I reduce the pulse width, right, smaller the pulse width, wider the sinc function, which means that broader the spectrum, so higher or larger the bandwidth. Okay, so from here we conclude that narrower the pulse, bigger the bandwidth. Okay, narrower the pulse, bigger the bandwidth. It's very critical point, and it's formulated in here, as you see. The bandwidth is proportional to 1 over tau. In some textbook, it's taken 1.2 over tau. So 20% marge is introduced. But you can use either. We usually will be taking 1 over tau in this course mostly. But if you see 1.2 divided by tau, then don't confuse, that's also correct. And if they use 1.2 over tau, then use 1.2 over tau in that calculation. Clear? Now, in the sink, as you see, the center is FC. So we got a sink placed at FC, the carrier frequency. So if I change the carrier frequency, the sink will be moving over the frequency. Okay? Here again, let's keep this in mind. There are 2 parameters which are very critical here. 3 parameters which are very critical in understanding this spectrum: the carrier frequency, the pulse width, and TP. And FC is the center of the sink function. Tau is the first null of the sink function. How about TP? TP describes the spacing between the discrete lines. So in practice, when you got a sequence of pulses, you will get a discrete spectrum. Okay, we have already shown this in communication systems course. So we got, you see here, some bars, some discrete components, and the spacing between any 2 discrete components here, you see, is 1 over PRI. So then if we increase PRI, then the discrete lines will be approaching to each other. Okay? If we make PRI smaller, then they're simply spreading. So they are far away from each other. So these 3 parameters then are critical for the spectrum, for understanding the spectrum of the radar waveform. Here is an example where we got real or realistic parameters, realistic values of the parameters for medium range air surveillance radar. Okay, you see the peak power is on the order of megawatt. Okay, megawatt, 1 megawatt. And the duration of the pulse is on the order of microsecond. So 1 microsecond. This is quite realistic. And the PRI, pulse repetition interval, is on the order of thousands of microseconds, so milliseconds. So then we can determine PRF, duty cycle, and also power attenuation, which is another parameter that we will be discussing later. The PRF here will be then 1 over PRI, which is 1 kilohertz in here. Okay? And duty cycle then is going to be 0.1%. So this radar seems to be transmitting 1 microsecond and then listen 999 microseconds. So most of the radars then, mostly they are listening. Okay, transmitting in a very short time and then listen long time. Okay, for the echo. So transmit 1 unit, listen 1,000 units. Transmit 1 unit, listen 100 units. Okay? But in some cases, this is not like that. For example, missile. missile systems where you have to trace every motion of the weapon, where you transmitting continuously, okay? Illuminating continuously and capturing or receiving echo signals continuously, because you the very little time difference or error would be very little for you. But mostly for surveillance radars, we transmit just 1% or less of time. Okay, now we'll be defining another critical parameter, unambiguous range. What is ambiguity in Turkish? Do you know it? Ambiguity means uncertainty. Ambiguity. Unambiguity, certainty. Okay? So if I say unambiguous, then that's certain. No, there is no unknown. It's quite clear when I say unambiguous. When I say ambiguous, then it may be unknown, it may be uncertain, something is uncertain. So then the definition here, unambiguous range, refers to something quite clear, deterministic or known or certain. Okay? Now let's consider a radar system. We transmit a pulse, and there is an object here, and another object here, here. When I transmit this pulse, it travels and hits this object and returns. And it continues. The energy is going through in that way and hits this object and then return. It continues again, hit this object and return, continues and then hit this object and return. So if I look at what I will receive with this one, I will, let's say this is echo 1, or target 1, 2, 3, 4, and 5. So what will happen? I will get an echo signal from the first one. This is the first target. The second one, let's say here. The third and fourth one, so just very close to each other. And then fifth one. Okay, that's how we see. Now, how can we determine the range then here? For example, if I choose the next pulse here, okay, transmitting pulse. So what will happen? What will happen? I will see this target and this target correctly, right? But when I get an echo signal, when I receive an echo signal with the third target, I may think that this is an echo signal due to the second pulse. Okay? So there is an ambiguity. Okay, there may be an ambiguity. Similarly, if I take a pulse here, an echo signal here, I may be thinking that this is due to the second pulse, not first pulse. Okay? So it goes in that way. So if you extend it and put many objects, then there is going to be an ambiguity. Then we have to determine a distance where we do not have any ambiguity. And that distance is simply called unambiguous range of the radar, which is proportional to the pulse repetition interval. So here, simply, this time interval is PRI, and PRI determines our unambiguous range. Beyond the PRI echo or range, we'll have ambiguity. Is that clear? And there are many ways to remove this ambiguity, to disambiguation, okay, let's say, and we'll be discussing them later. But at the moment, just think about this scenario, and I'll be showing in the next slide in detail. If if I have second, third, or fourth time echo signals, then there is going to be ambiguity. And unambiguous range is defined as simply the speed of light times pulse repetition interval divided by 2. So that's the equation that we defined in the beginning, actually. That equation is an unambiguous range equation. Beyond this range, there will be ambiguity. And here we see a picture showing range ambiguity. As you see, we transmit a pulse here. Okay, this is the first pulse. This is the first pulse, second pulse, third pulse, and fourth pulse. These are the pulses that I transmit from the radar. Okay, then I will see an echo signal from the nearest target, target A. So here is target A. And this is correct, right? This is correct because why? It is within unambiguous range. Okay, I'm sure about that. That's right because I know the unambiguous range. So what will happen if there is another target B, which is far from A, then the echo signal due to the first transmitted signal will be coming after the second signal, second pulse, sorry. Okay? Then this is going to be ambiguous echo, right? We may think that this is an object just like here, for example. Why? Because it's near, you see, it's closer than target A. If I take pulse 2 as reference. But actually, that's an echo signal due to the first pulse. Okay, so we can extend this. We can take C. Then there is going to be, of course, I will get an echo signal due to the pulse 2 from target A. And then when I transmit the third pulse, I will get another echo signal from B. And then here, it appears another echo signal. I may be thinking that that's due to the pulse 3 or pulse 2. Who knows? Maybe there was no object there, but suddenly it appears. So you see there are ambiguities in here. Is that clear? Now we can reduce ambiguity by different techniques, and we'll be discussing them later. Unambiguous range, we can simply write the equation with unambiguous range and PRF, which was CTP over 2 or C over 2FP, okay? And we can make a graph like this and simply read unambiguous range versus pulse repetition frequency. Is that related to the bandwidth or band? No, it's just about pulse repetition interval, right? Nothing else. And in the textbook and in some other reference books, you may see nautical miles, by the way, NM, which is 1.85 kilometers. There is also mile, okay? You may know that. It's 1.6 kilometers. So please be careful. Don't confuse nautical mile and mile. Mile is 1.6 kilometers, while nautical mile is 1.85 kilometers. And most of the sea community use nautical miles. In sea platforms or radars, they use nautical miles. Here is an example of airborne fire control radar, which is installed F-16. You may know F-16. There are several series of that aircraft, C, D, B. Now, as far as I know, the last version is D. There is a complicated radar system installed on F-16. in many variants of F-16. Maybe newer version might have different radar, but as far as I see from the open literature, for airborne fire control radar, it's a multi-mode radar system, okay, multi-mode, which means that it has several modes, okay? Since we have limited space on a platform, we have to make things smaller and low weight, low power, because power, size, and weight are critical for air platform, which means that that should be very complicated, okay? So smaller, so size, weight, and power, SWAP. This refers to complexity. More complex system you have to design to make smaller size, smaller weight, smaller power. And multi-mode here refers to different PRF range, okay? Low PRF mode, high PRF mode, and medium PRF mode. So for low PRF mode, which corresponds to high PRI, okay, air to surface engagements. So if the platform, if F-16 wants to see something on the surface of the ground, usually the distance is long and the objects on the ground are slowly moving in reference to the platform, then it uses low PRF, okay? On the order of kilohertz, and typically here is 500 hertz. Okay? For high PRF, where it looks into velocity, speed of the object, and it's used for air interceptions. Okay? It uses 15 kilohertz. You see the difference, 500 to 15 kilohertz. Okay? And it's for air interception. It means that another platform, another aircraft, another missile, or helicopter or UAV. So fast moving objects nearby, okay? These are dangerous. So you have to check it, and you have to continuously check whether there is something around you, and you have to measure, moreover, its speed, okay? Because when you know the speed, you can estimate where it is or how much time you have. Or if you want to fire a weapon, you have to determine speed and position together. And there is also medium PRF, search mode. It increases range and angle information. It's somewhere between 0.5 to 15 kilohertz. Of course, there has been some enhancement on the system. Simply, depending on the requirement, your mission, you may use low PRF, high PRF, or medium PRF. I mean, there is, we couldn't comment on which one is better. There is nothing better here. It's about requirement. I think if you want, we can give a break after this example. This is early warning radar system, which is called talking. Early warning means you want to see an object, an hostile weapon or system, far away from you, as early as possible. For example, let's say in Turkey, if, for example, we are interested in an aircraft in, for example, our neighbor Greece, we want to see that as early as possible when it is taking off. For example, in around Athens, which is 200 or 300 kilometers away. But you have to see that as early as possible, and then pass this information to another radar system or weapon system to trace it if it is moving to you. Okay? Usually, early warning radar systems use very low PRF, of course, and the range is not critical here, actually. Resolution is not critical, but it's rather, the approximate distance and the existence of the object is more critical. It uses 150 to 170 megahertz band. This is operational band, so it is about FC, the carrier frequency, or cosinusoid. And the range is 500 to 600 kilometers, depending on the position, location of the radar and the target. It uses 100 to 200 hertz, quite low, and we talk about a power rate of less than 1 megawatt. It's a very old system, introduced in 1950s, and usually it's used for high altitude aircrafts, overseas, for example. You can see a picture of that system in here. Okay, let's have a break here. Is there any question? Okay, let's continue. I forgot to talk about a parameter here. One of the students warned me, power attenuation. Power attenuation is the ratio of the transmitted power and received power. Let's say my transmitted power is 1 megawatt. Sorry, 1 megawatt. And let's say the received power is 1 microwatt. Usually the transmit power is quite big and the received power is quite small. And then PT over PR will be 1 megawatt divided by 1 microwatt, which is 10 to the power 6 watt, divided by 10 to the minus 6 watt. Watts cancel out. Then the result is going to be 10 to the power 12. Okay? Not watt, 10 to the power 12. That's ratio. This is equivalent to 10 log 10 to the power 12, which is 120 dB. Okay? So in dB, it's 120 dB, while in ratio, 10 to the power 12. So if I transmit 1 watt, then the received signal will be 10 to the minus 12 watt. So I transmit 1 watt, then the received power will be 10 to the minus 12 watt. Okay? This is not about the details of attenuation here. There are antenna gains, cable loss, and path loss especially, and the scattering properties of the targets. All are ignored here. We just look at the parametric differences only. Transmit power and receiver power, how much they are difference, okay? What is the range of these power ratios, okay? It's quite big, as you see, 10 to the power 12. Okay, let's continue with that slide. Okay, monostatic and bistatic operations. In a radar system, we got a transmitter and receiver. Usually, they are co-located and they work together in coordination, and it's called monostatic operation because transmitter and receiver are co-located. They are on the same platform. Then it's called monostatic operation. On the other end, we may also place a transmitter and receiver at different locations. We can position them separately and then synchronize it. So there is a synchronization usually here. And we simply here use bistatic operation. Okay, we can also define then multistatic operations where we got a network of radars, network of transmitter and receivers, or network of radars simply. We can, for example, use M transmitters and N receivers. They are coordinated, placed separately, different positions. If they are coordinated, synchronized, then the capability of the system will be much higher than monostatic or bistatic radar. But of course, that's quite expensive and complex. Range resolution and cross range. Okay, in this slide, you see there is a picture here. From the picture, you can see the range and cross range axis. Here is the range axis. So you see two targets are closing to the radar. Let's say we got a radar here, and the resolution where which is defined as the range of the distance at which we can separate two targets, close targets. Okay, here range resolution measured over the range R. Okay, the cross range is simply perpendicular to the range axis, and it's rather related to the antenna properties of the radar, beam width of the antenna, especially in azimuth or elevation. So cross range might be either azimuth or elevation. Range is simply on the distance. Okay. Over the range, mostly we divide the maximum and minimum range into n beams. Okay, n beams. Okay, and this beam is proportional to the range resolution, and next slide will be defined range resolution. Of course, higher the range resolution, so the number, as a number, smaller the resolution, is better the performance of distinguishing of two targets closing to each other. Okay, here we see we got a pulse, radar pulse, whose duration is tau, you see, over time. In space, this corresponds to a distance of c times tau. C is the speed of the light. So if I consider 1 microsecond pulse, this is going to be a range over space of 3 10 to the 8 meter per second times 10 to the minus 6 seconds, which is 300 meters. So 1 microsecond pulse in space is spread over 300 meters. Okay? So if I have two objects over 300 meters, then I cannot detect them, right? So the position here is critical. This spreading of the energy is critical. Okay, let's consider two targets here. Target 1 and 2 at range R1 and R2, and we got an incident pulse of c tau. That pulse is simply hitting on the first target first, and then the second target, while it's reflecting from the first target. It's some of the energy will be still traveling to the second target, and then reflect from the second target. So there's going to be overlapping of the echo signal energy. Okay, and then in order to separate these two targets, the distance will be half of the energy over the space, right? Logically, we can think about this. Half of the energy is hitting on the second, half of the energy will be reflected from the first, okay? So if the distance is greater than half of the c tau, then we can separate them. That's the idea of range resolution, and it's mathematically written in here. C tau over 2 is the range resolution. Okay? Mostly, tau is 1 over b, the bandwidth. Then we can also write range resolution in terms of bandwidth, c over 2b. Okay? Here's an example, range resolution for early warning radar and fire control radar. We have already shown these radars in previous slides. The pulse width for early warning radar is 10 microsecond, while for fire control radar, it's about 0.3 to 4 microsecond. Okay? And for search mode and tracking mode, you see the pulse width are different. So I simply take 0.3 for tracking and 4 microsecond for searching. Okay, so here is the pulse width. Here is the pulse width, tau. So we can determine range resolution for early warning radar as 1.5 kilometers. So if I have two targets within 1.5 kilometers, I will see them single target. Is that critical for early warning? No. I'm not interested in the details. I just want to know whether there is a target there or not. Even the precise distance may not be critical. The most critical thing is simply deducting that target as early as possible. Okay, so at long distance, we want to detect them. On the other hand, for fire control radar, where I just fire or launch a missile, for example, I want to know the target position, right? And precisely, angle, position, and speed, these are critical. So I have to have a very good range resolution, okay? And here we see it's about 45 meters in here, maybe less than that. There are some other parameters. 45 is not a perfect number, but that's quite good. Most of the aircrafts, for example, F-16, the distance will be more than 30 or 45 meters, depending on the speed. Here's a problem from the reference book, Mahafza. We are given an ambiguous range and bandwidth, which is 1 over tau, as you may know. PRF, PRI, delta R, here, then it requires range resolution, you see. Right? And tau, the pulse width. Okay? I'm sure that you can easily solve it. And resolution cell. Now we defined range resolution. There is a resolution in angle, so in azimuth and elevation. These are related to antenna beam widths in azimuth and elevation. So these are antenna specific parameters. Narrower the beam width of the antenna in azimuth and elevation, better the range resolution, angular resolution in azimuth and elevation. When we take the resolution in azimuth and elevation and range, we define radar cube, okay? Radar cell or radar cube sometimes. This is also defined for signal processing, but mostly we say radar cell anyway. So here is the radar cell. Okay. This is just like cube, not exactly a cube, just a volume in space, okay? Now, in next slide, we'll be showing how to calculate that. For this, we simply take a radar beam. Let's say this is azimuth. And we got an angle here, let's say alpha, the distance is r. Then the length of this arc is going to be what? Alpha times r. So higher the range, you see, higher the arc length, okay? Which means that the radar cell will be getting bigger with the distance, okay? Getting bigger with the distance. But in range, it's constant. Range resolution is constant. But the resolution in azimuth and elevation are getting increase with the range, okay, due to this arc length. Here we have an early warning radar again, 1 gigahertz, PRF is 300 hertz, pulse width is 10 microsecond, and antenna beam width is 2 degrees and 5 degrees. 2 degrees in azimuth and 5 degrees in elevation. So this antenna seems to be better in azimuth, okay, than elevation, because the beam width is narrower in azimuth. We convert these degrees into radians. They are simply 0.035 and 0.087. And then we determine range resolution. Range resolution is easy, tau, right, times C over 2. On the other hand, for azimuth and elevation resolution, we use the distance R times alpha in radian. Okay, distance times alpha. And we see a radar cell of size 1.5 kilometer in range, 3.5 kilometer in azimuth, and 8.7 kilometer in elevation. Okay? So simply we can think about this like this. Right? No, it's narrower in that direction. I'm sorry. Just like this, you can consider. Okay, so wider in elevation, narrower in azimuth, and the range is quite small compared with the other two dimensions. Okay, now so far we have learned some basic parameters of a radar system, especially radar waveform. Now we are going to derive a simple radar range equation. And in the remaining subsequent 2 lessons, we'll be discussing radar range equation, by the way. That's the fundamental concept usually taught in a radar system course. And we are gonna follow that. So next lesson and the lesson after the next one will be on radar range equation with some other parameters that help us to build the system actually, how a radar system operates. Okay, let's consider a radar system which has a transmit and receive modules. They are coordinated, working together. And the transmit power is PT, and the gain of the transmitting antenna is G, and the receiving antenna is also G, let's say, so the same antenna, for example. Then the power in space will be the transmit power times G, okay, which is called effective radiated power, or ERP. Okay, this EPT times G is called ERP. Now, this power travels in space. Okay, travels in space. At any distance r, if we consider that that's spreading in space, the power density in space will be the transmitted power times G divided by the area of a sphere. Okay, we can imagine a spherical surface around the radar. Then the power density at a distance r will be the PTG, so the transmitted power, divide the surface area of the sphere, which is 4 pi r squared. Okay, so this is sphere's area, surface area. So we divide that number, PTG over 4 pi r squared, then this power density hits on the surface of the target. Okay? So then larger the distance, smaller the power density hitting on the surface of the target. Okay? So how much of the power will be reflected back? That's the question. Or how much power will be on the surface of the target? It's about the cross-sectional area of the target and also the geometry, frequency, some other parameters. Then we define radar cross-section, sigma. Okay, it's about not a geometrical cross-section, but radar cross-section, which is determined by electromagnetic interaction effects, properties, discontinuities. It's quite complicated parameter. It's not easy to calculate, estimate. And anyway, that's a cross-sectional area, so meter squared simply. So the power on the surface of the target will be PTG over 4 pi r squared times sigma, okay, which is the RCS of the target. And it's dependent on the target, okay? For example, your RCS is different from you. Your RCS is different from you. Okay, all are different. Notebook has different RCS. A bird has a different RCS from another bird. So that's specific to the target. And then this is going to be the power of the target actually, and then reflected back. Okay? Again, travel to the target with a distance r. Then the power density at around the antenna of the radar will be PTG over 4 pi r squared times sigma divided by 4 pi r squared. Again, this is the first area. So you can imagine that the target here behaves like a transmitter. Okay? Like a transmitter. And then this power density, that's again power density, will be picked up by the antenna. How much will be picked up? It's dependent on the surface area or effective aperture of the antenna. Again, that's just like sigma of the target. Okay? But that can be calculated. So then the received power will be given with this formula. Okay, PTG AE times sigma divided by 4 pi squared times r to the power 4. Okay? Now, what is the maximum distance that we can achieve is simply it can be calculated by minimizing the received power. The minimum power that I detect, that I can detect, will determine the maximum range. Okay? So if I equate received power to the minimum detectable signal, then I will determine the maximum distance, which is the radar range. By the way, range here stands for both distance in Turkish menzil. Exactly, okay? Menzil. Here, the range stands for in Turkish menzil. So, radar menzili. Then we write maximum range. So, radar menzil. with this formula. Now, the antenna parameters are related to each other. We can write gain of an antenna as 4 pi AE divided by lambda squared, where lambda is proportional to the operational frequency, which is FC usually. And this can be written as C lambda FC, okay? It's a simple formula that we may use from communication systems. So lambda here is that lambda, operational frequency. Then I can write maximum range with this formula. So there are two equations here. One is given in terms of lambda and AE. The other one is given in terms of G and lambda. Whatever you want, you can use. Okay? Sure. We'll be talking about that later, but in the textbook you can see how we write AE, okay, which is rho times A. It's not given in here, but you are right. Maybe we have to add it into here, not later, but we'll be discussing that later. Here's the formula that we use. Efficiency times the cross-sectional area of the antenna. Okay, it seems that you studied well. Good. But it's easy, right, to understand. When you read a text there's a text about that with some samples. Just read it and you understand. Multiply the size, that's it.
Ama yani bizim düşündüğümüz bir hiçbir yerde bulamadık sorularda.
That's right. That's right.
Dediğimiz formda zaten geyine ilişkisi olduğunu.
That's maybe I have to correct that part because in the textbook that efficiency is discussed in the first chapter, but I usually discuss that later when I extend the range equation. Somehow this might be in that way beneficial for the student because they have to look at the textbook. The material may not be enough to understand everything. So if you look at the textbook, you may see the details. And also note that I skip some of the subjects in the textbook. We are not sticking to all subjects. We are not responsible for all subjects in the textbook. There are some advanced topics there. There are some minor issues that we have to skip. And please follow the lecture notes, only PDF material here, and then look at the material related to the PDF material only, not the others. Do not spend time for other materials. Of course, voluntarily you can study that, but you are not responsible in examinations, okay? And please warn me if you see such a case. I mean, you come across a question in examination that is not discussed in PDF material. Then you can warn me, and then if there is something wrong or mistake or missed something there, then I can consider this in grading. Okay, now let's see this equation. In order to double the maximum range, so in order to get an R max prime, which is 2 times R max, okay, you have to increase the transmit power 16 times. Why? Because the transmit power divided to the power of 1/4. So if I say the PT as 16 PT, then the power of 1/4 will give me 2 PT, right? So 2 R max, not PT, sorry, 2 R max. Clear? So the powers are critical here. If you want to extend the range, you have to increase something, or you have to decrease something in the equation. For example, in order to extend this maximum range, you may reduce minimum detectable signal, right? That's another way. or you can increase wavelength, or you can increase gain of the antenna. Now the question here is critical. Unambiguous range and maximum range. So I got an equation here for maximum range, and also we got an unambiguous range we defined previously. So which one will be used, or how do we relate them? That's a question that we have to think about. I'm not asking you to answer now. I'm not going to answer. I will recommend you to read about that, and we can discuss that in the next lesson. So here is the pulse radar operation, very simplified block diagram. At the end of the semester, okay, listen, at the end of the semester, hopefully, you will build such a radar in the laboratory and see how it operates in the laboratory. You will detect some objects and see the object's motion, for example. Okay? So what do we have? Here is the transmitter. Typically, it consists of a waveform generator connected to a power amplifier, okay, PA, with a pulse modulator, so a pulse sequence, just a switching circuit that switch the pulse power amplifier on and off. Okay, that's the simplest way to generate that, but there are some other ways. And then we got a duplexer. Duplexer transmit a signal coming from the power amplifier to the antenna. If there is a signal picked up by the antenna, it passes through that signal to the receiver. So here is the receiver. Okay, so duplexer is very critical. It allows us to operate a radar system with single antenna, both transmit and receive together at the same time. We are transmitting and receiving together. Okay. What do we have at the receiver? We got a LNA, low noise amplifier. We got a mixer with an oscillator here. And the frequency of the received signal, let's say FR, the frequency of the local oscillator is FL. Then here we'll have intermediate frequency, FIF, which is the difference between FR and FL. Okay? Intermediate frequency. IF stands for intermediate frequency. Usually it's on the order of several megahertz or several tens of megahertz or several hundreds of megahertz. Okay? Not typically gigahertz. Usually this amplifier is designed as a match filter, which increases the signal to noise ratio. So here, SNR is maximized at the output of the match filter. And then we got a detector. Typically, that's a diode detector. You may remember envelope detector in communication systems. If you look at the lecture notes, you will see envelope detector. So that's the same concept. So here we got a pulse type signal at the output of this detector. Now we got a cosinusoid here, while here we remove this cosinusoid and take the envelope only. Okay, so the waveform that we have shown in the first slide, just a rectangle, but not perfect rectangle. That's a distorted rectangle, but there is no cosine inside. So we got an amplifier typically to amplify the signal and then make a decision by threshold. If let's say this is threshold, if the signal exceeds this threshold, we declare that there is a target. If it is below that threshold, that's declared as a noise. It's called decision stage, decision thresholding. So that's a simplified operational block diagram of a radar system. There are two main things inside actually. For example, an antenna, you have to move your antenna. There should be a servo mechanism to control antenna and sweep in azimuth and elevation, for example, together or just one dimension. That's one thing. There should be power circuitry, power supply to power all of this. There should be some control circuits to switch between two components or to synchronize different components. So it's a quite complicated system, actually. It depends on the requirements. Sometimes we have to build a very big radar system. Sometimes we got a chip only, just use a chip to detect movement, for example. It's highly variable depending on the requirement, mission. Here is the radar frequency band. So it's about, you remember cosinusoid? Okay, this was the radar waveform that we have drawn previously. This was the rectangle pulse, you see, pulse train. It's a very typical waveform. Now, this frequency is the frequency of this cosinusoid, okay? The range of this frequency, carrier frequency. For HF, that's 3 to 30 megahertz, which is the lowest band that we use, and usually some radar systems called over the horizon, OTH, okay? They use HF bands. As you might understand from the name, over the horizon, even if we got the curvature of the Earth, this type of radars can detect objects beyond the horizon. Okay, it's interesting, beyond the horizon. How? That's due to the fact that those HF signals can travel over the horizon and then reflected back from the objects over the horizon. Okay? So that the range is quite long. Let's say an horizon might be, let's say 30 kilometers to, for example, 200 kilometers if you elevate the antenna. But this might operate over the horizon 100 kilometers more, so 300 kilometers, 400 kilometers. So you can detect the surface, especially platforms earlier. Okay? That's not that easy, of course. That's quite complicated system, but that's possible now. We got the VHF radars, again, early warning radar systems, UHF also, and we got radar altimeters, just like aircraft, for example. They have to determine the height altimeter from the Earth. There are some pressure-based techniques, but this radar type altimeter is more effective because it's not dependent on other things. They use simply S and C band, so altimeters. And here we see early warning radars here. And in meteorology radars, we usually have C to X band. And after about 8 gigahertz, we see military radars. Usually these bands are designated. So if you want to build a military radar, you are given a specific band. and you have to use that band with some conditions, let's say. Otherwise, you couldn't use it. If you use it, of course, you can design your radar at any frequency, but you couldn't sell it, okay? If it is not, you know, meet the standards. Now, we got radars up to 110 gigahertz, by the way, especially used in automotive applications where we have automatic collision detection systems. I mean, one vehicle can detect others so that no collision happens. And here is, we see new band designation. Now there has been a change on the designation of the bands. Instead of this, we might see this ABC convention. But still, this is quite popular. The old one is quite popular. You may see this designation in different places, so please be careful. So one may use, for example, E-band. In here, there is no E-band, which means that that guy is talking about this ABC designation, okay? And here is the list of the exercises, problems. From page 27 to 28, there are 6 questions, and I simply recommend you to solve these problems. When you solve them, you don't worry about the post-test, okay? Probably you can do that easily if you solve these problems. And in the textbook, there are some challenging problems too. So I recommend you not to try them. Instead, focus on this, solve them. If you are still, if you have still interest on other complicated topics, then you can try. Okay? So we are going to be selective anyway in the textbook. We are not studying every subject in every chapter. We select some topics, we select some level of problems or material there. We are only using those materials and we are only solving those problems, okay? I think it's enough. Thank you.